Hello. Today we're going to continue with our discussion on mathematics of finance. We can start with reviewing compound interest, which is section 5.2 in the text. Last time we talked about how compound interest differs from simple interest. We said that compound interest is interest that earns interest. It's reinvested back into the account so that not only your principal is making interest. So in this example, we're depositing $1,000 into a savings account at 5% interest. That's what we earn. It is deposited and reinvested every year. So as we earn interest, that interest gets reinvested into the account, and then the next year it will earn interest. At the end of 5 years, we're being asked how much money will we have accumulated. So we're going to use our compound interest formula. This formula down here is our simple interest formula. At the end of the first year, it actually ends up being the same as our compound interest. But the second year, the principal value changes. So instead of only being $1,000 like it was when we did our simple interest, it's now $1,050 because we've earned $50 the first year. Having that interest earn interest is compounding the interest. We could go through and calculate it 5 times to figure out the 5th year, or we can just use the formula that we see down here, where we've plugged in 1,000 for the present value, 5% for the annual percentage rate, and NT, we're only compounding once a year, so it's a 1, and T is 5 years. So that's how we ended up with $1,276.28. Often, banks will pay out interest more than once a year. So you may invest and get back monthly interest or quarterly interest or semi-annual interest. So as that amount changes, that's when we have to utilize that N for number of compounds per year and T for our time. This table here is showing how you can accumulate more interest with time as you have more frequent compounding. So the first column was our simple interest calculations, where we're earning 5% per year only on the $1,000 principal. In this middle column, we're looking at, we have $1,000 invested, 5%. It is compounding annually, which means that that interest gets reinvested. In this last column, we have monthly compounding, which means that every month, whatever interest is earned is now added to the principal, so the next month you're earning interest on that interest. So as you can see, at the end of 5 years, how much more you have accumulated. These are the formulas that you can use to get to that 5th year without having to go through 1, 2, 3, 4, 5 years worth of calculations. Going over these variables once again, FV is our future value, PV is our present value, R is our annual percentage rate, M is the number of compounds per year, and T is time in years. This formula can be written as you see in the second formula, where I has replaced R over M. I now represents the per period interest rate, per compounding period, and N represents MT, which is the total number of compounds in that investment period. Remember that M is how many compounds happen per year. So that means if it's monthly, that would be 12 times a year. If it's quarterly, it would be 4 times per year. If it was semi-annually, it'd be twice per year. If it was daily, it'd be 365, unless the problem tells you to use 360. You would use 365. So here's a quick example. To find our future value after 5 years for a $10,000 investment that earns 6% interest, first we're going to assign all our variables. We have PV is 1,000. We've got 0.06 for the interest rate. Remember, you have to write this as a decimal. We have M equals 12 because it's invested monthly and reinvested monthly. And we have T equals 5 because we're looking for a 5-year investment. When we plug all that into our calculator, we get $13,488.50. Now I do want to point out that if you're plugging this in all at once, you are going to want to put an extra set of parentheses around this fraction and also around the MT that's in the power. Otherwise, you won't get the correct answer. It's a good idea to try practicing putting this into your calculator to make sure that you end up with the $13,488.50 if you haven't already done so. Here's another example. This is example 1 out of the text. We have the American Express Bank of Canada in 2008 was paying 2.4% interest on savings accounts. It's compounded quarterly, so that means my M is going to be 4. We're looking for the future value. If we have a present value of 2,000 and we're depositing it for T equals 6 years. What is the total interest paid per period? So in order to find the interest, what we're going to do is we're going to find how much total money do we have, and then we're going to subtract out the present value, which is the amount that was invested. So using my future interest formula, plugging in 4 for M, 6 for T, 0.0240 for my rate, and 2,000 for my present value, I come up with $2,308.77. Now, in order to find the interest, I'm going to take the future value and subtract the present value. So I take my total amount of money and subtract out how much I had to begin with, and I end up with $308.77. So be very careful when you're reading these. You want to make sure that you're answering the question. It didn't want to know how much total money we have, principal and interest. It wants to know just how much interest. How much did we make on this investment? So this example illustrates the concepts of the time value of money, which means some amount of money that is received now is usually worth a different amount to us than the same amount received in the future. So what that is saying is that we can say that $2,000 received now is the same as receiving $2,308.77 6 years from now. Because we received the $2,000 now, we can turn it into $2,308.77 by the end of 6 years. So we say that what is equivalent value at present when we're talking about future money. So just like for simple interest, we can solve that formula for present value, and that will give us a formula that we can then plug in all of the information we have, and we can know how much money do we have to have at the beginning so that we can invest and get the future value that we're looking for at the end. So these are the formulas. Once again, there's 2 forms of the formula. This one is going to have your R and your M and your MT. This one is going to have your I and your N. And here's a quick example using it. Here we're looking to find the amount we need to invest that will earn 12% per year, compounded annually, so that we will have $1 million in 20 years. So we're going to have a future value of $1 million. We've got our rate is 0.12. M is once a year because it's compounding annually. and time is 20 years. So now I can plug in those values into my formula, and I end up with $103,666.77. When you calculate this, make sure you calculate this inside parentheses first, and then raise it to the power of 20, and then you can do your division. If you're going to put it all into your calculator all at once, put parentheses around the whole denominator. That will force it to calculate the denominator before it does the division. Another way to state what we've just calculated is that $1 million 20 years from now is worth only $103,666.77 to us now, if we are able to invest 12% investment. We have mentioned that bonds pay interest until they reach maturity, at which point it'll pay you back an amount called its maturity value. Sometimes we call it its face value or par value. There's two parts, the interest and the maturity value. They can be separated and sold and traded by themselves. A zero coupon bond is a form of a corporate bond that pays no interest during its life, but like the U.S. Treasury bills that we talked about with simple interest, they promise to pay you the maturity value when it reaches maturity. So zero coupon bonds are often created by removing or stripping the interest coupons from an ordinary bond. We also can call these strips. They sell for less than their maturity value, and return on investment is different from what the investor pays from the maturity value. Although there's no interest actually paid, we tend to measure that return on interest as a interest, thinking of it as an interest rate, which would make the selling price the present value and the maturity value the future value. So we would still use the same formulas, but we could apply them to our zero coupon bonds. Effective interest rate. Now, last time in class we talked about how we could use our future value to compare two investments to see how much money we'd have at the end of the investment period, and then we would just select the one that would give us the most. Another way of deciding between two investments that may have different interest amounts and different compounding periods. You can essentially create a level playing ground by calculating this effective interest rate. So in this case, my R nominal is going to be whatever my annual percentage rate is that's provided, and the M is still going to be the number of compounds per year. When I calculate this, this will convert it over to an annual rate. So that way it's apples to apples. So if I was comparing 2 or 3 investments, I could calculate what the effective rate was, and then I could compare them, and whichever one is going to have the highest effective rate, that would be my choice or my recommendation for that investment, because I'm going to earn the most money. So here's a quick example on that. If we wanted to calculate what the effective interest rate was for an investment that pays 8% per year with interest reinvested monthly, I'm going to set our nom, or nominal, as 0.08 for the 8%. M is 12 because there's 12 months in a year, and I just plug it into the formula and I end up with 0.0830 or 8.30%. So what that means is that 8% per year invested monthly is the same as earning 8.3% annually. So it's converted it over to annual interest rate. And that is the end of section 5.2. We have a quiz that's going to be coming up on 5.1 and 5.2. It's due next class, so you should be working on that, and you can either pass it in class or you can submit it online.